So first off, I just want to say thank you for letting me back on this stage. This is a great conference. I've been coming here for many years, and I just want to say thank you for everybody who organizes this. I've now am in the process of leading a conference, and I'll share that at the end of this, and I know how much work it is, so please be sure to thank everybody responsible for this. So with that, I'm here to talk about containers. Quick show of hands. How many people here are familiar with containers? The topic has come up quite a bit since I've been here, and it's fantastic to see. When I first started talking about this, just a couple hands went up, and now it's pretty much the whole room. So it's good to see that there's so much uptake of it. So let's start off with introductions. So hi everybody, that's me. Greg. I'm the founder of a company called Sylabs. We're about a year and a month and a half old at this point. And luckily, we've been growing fantastically. I'll talk a little bit more about that in the end. I believe this was in the community track, so I'll try to keep the sales part to a minimum. But CEO, I've learned, is an interesting title because it means I went from engineering to salesperson. So I'm going to try not to sell anything for the duration of this, but at the same token, it's important for business. So anyway, previous to this, I spent about 20 years working at Lawrence Berkeley National Laboratory. That's a Department of Energy facility, and I spent that time as an HPC systems architect. In that role, I worked with a lot of users, a lot of different types of applications, and got the opportunity to really understand what kind of problems that they needed to solve, and then build systems that solve those problems. So with that visibility, I saw some opportunities to create projects in the open source community as well as contribute to existing ones. I've been very lucky along my career to be part of some fantastic stuff. So another show of hands, how many people here has heard of Warewulf, the cluster management system? Very cool. So I founded that in 2001, still lead that project today. It is the provisioning basis of OpenHPC, among other things. Another project that I created, a little Linux distribution called CentOS. A couple people know of it? Okay. And then a couple other things since then. Most recently, though, a container system called Singularity. Luckily, I don't have to ask if you've heard of it because it came up a couple times in other talks, which is really exciting. So, okay. Let's just make sure we're all on the same page in terms of what a container is. So I'm going to go kind of down to the most basic level. Most people in this room already have a good understanding of containers. So really, I'm not going to spend much time on it. It's an encapsulation of user space. In a Linux distribution, you've got your kernel space, you've got your user space that sits on top of that. The container is the encapsulation of that entire space. It includes applications, it includes libraries, potentially data, configurations, all of that we're going to put inside of a container, right? And then we're going to close up that container. In Singularity speak, we can sign that container, we can guarantee immutability, and we can move that container around. So we can move it to another host, for example, and then run applications from that container as if they are native on that host. All right, so it gives us some really cool abilities. Additionally, from the runtime engine, it gives you the ability to do other things like isolate or integrate with the underlying operating system, hardware, and kernel. So in a very high nutshell, that's what we're doing. Okay, so start talking about Singularity. Primarily differentiates itself in a couple major categories. First is the runtime engine. Runtime engine in Singularity is designed for performance. We have the ability to support things like the security model that most HPC centers require in order to allow their users to gain access to containers and some of the privileged system calls and whatnot necessary to leverage this technology. Additionally, there is the container format. The container format is, in Singularity, it is kind of unique. We're doing this different than pretty much every other container system out there. I'll go into some of the specifics about why we're doing it differently. There's some certain benefits and whatnot, but one of the key pieces is that we can take the standard container formats, which could be Docker or OCI, and encapsulate them, and then offer additional features on top of that, on top of what they currently offer. So that's one of the really cool facets of what we're doing in this container format. So let's start talking about that. in terms of what the architecture of that file looks like, you can see it here. It's modeled originally after the ELF binary format in Linux, but we've kind of taken it a little bit in a different direction since the original conception of it. We have the ability, as you can see from the top, very top, we've got a global header, we got general metadata that's container-wide, and we got a linked list of object descriptors, and those object descriptors have pointers and references to other portions of the file that have certain bits of data in them. So you can see, I'll call your attention to the immutable runtime container image. This is the actual runtime image that is executed when the container is run, but beneath that we have something really cool. It's a signature block. We can use the signature block to guarantee immutability and to provide accountability as to who signed it. So I'll talk about that more in just a moment. As I said, we can encapsulate the OCI and Docker standards. And when we do that, we could take all of the complexity and moving parts that there is in the standard OCI registry and Docker registry, as well as the root-owned daemon components, the parts that basically take all those layers, splat them out to the file system, and then stitch them all together at runtime. We could take this whole thing and encapsulate it inside of a single file container. And there's certain really cool benefits that you get when you do that. One of those is performance. So this is a test of basically encapsulating Python, putting that Python application into a Singularity container, and then comparing that Singularity container running local on a shared file system to the actual install of Python running on that same shared file system. And what you can see is, Python's pretty well known for doing a lot of metadata lookups, right? And shared file systems, especially parallel file systems, are notoriously bad at dealing with that sort of stuff. So if you encapsulate that and you consolidate all of those metadata lookups, you can actually get a performance increase, especially as you start going out to scale. So this is an example of that. You can see the more number of concurrent interpreters that we're running at once, right, the greater the delta in time. This is logarithmic both ways, by the way, so that delta is actually really huge. And it keeps getting worse as you keep scaling up. I talked about the signature block inside that container. This means that you can very, very easily sign that container. And when I say sign the container, I mean literally you are basically taking a signature of the entire immutable portion of the container runtime. And this gives you some really cool benefits because, well, first off, the way we're approaching this, it's incredibly simple, right? Normally when I start talking about cryptography, about half the room starts, getting nervous, right? It's like math in high school, right? A lot of people don't get cryptography very well, right? Including me, right? I know how to SSH into systems, and that's pretty much it, right? But we've made it incredibly simple, as you can see, right? You can do a Singularity sign pointing at your container. If you don't have your public-private key pairs already generated, Singularity will walk you through that. It'll give you the option of pushing those keys, the public keys, out to our key store, which is a public repository up in the cloud, right? Then you can take this container and you can go anywhere with it. Doesn't matter how you get it, right? You can email it to somebody, you can copy it on Google Drive, you can put it in what's called our container library and pull it out of there and bring it somewhere else. You can drive it all the way out to the edge. And you can do a Singularity verify and always guarantee you're in exactly that environment. But it even does one step further. Not only does it guarantee the immutability, but it also gives you a point of accountability, right? So in this case, you can see I signed this image. So if you trust me, I don't know why you would, but if you trusted me, right, you can trust the images coming from me. If Ubuntu signed an image, you can trust that image, right? Especially right now, we're seeing some really interesting security issues coming up with containers. Anybody been following some of like the Docker doomsday? A couple of people, right? It's culmination of few things going into that, but one of them is untrusted containers, right? So this provides a solution for that. So what have we done? We have taken the application environment, we've taken the container, the whole user space, and we put it into a format that's incredibly easy to move around, it's easy to trust, it's It's easy to support, right? And we can now move it around, and we can now bridge gaps between various resources. So whether you build it on your laptop or you build it on a remote system, you can bring it now to your HPC system, right? You can bring it to local private clouds. You can bring it to your NVIDIA DGX, right? Anywhere. Or you can bring it up to public clouds. You know, whether it be Google, whether it be Rescale, Uber Cloud, right? AWS, Microsoft Azure, right? They all support the format. Some of them support it more than others, right? Rescale and Microsoft Azure, you can take that container format, the CIF, and just upload it to them, and they'll figure out what to do with it, and they'll make it work. When we're talking about running jobs on HPC resources, there's some considerations that we have to take into, well, consideration, right? So one of those is, and we like to call it, is we like to integrate versus isolate. And integration with the underlying operating system is very important. If you want access to things like GPUs, InfiniBand, right? You can't isolate yourself away from that. And that's what most of the container systems out there are focused on doing. They're focused on isolation to give security, right? Well, we need to integrate with the underlying operating system, but not give up security. So it's kind of an interesting paradigm. So we do that via several different ways. One is we have a container runtime that basically supports all currently supported Linux distributions. So if you have a Linux distribution in production going from RHEL 6 all the way across Ubuntu, whatnot, Singularity is going to work right away. Just simple install, one package. It's also designed right from the beginning for efficiency and performance. Startup speed on a Singularity container is in the thousands of seconds. Thousandths of seconds, excuse me, not thousands of seconds. That would really suck if it was thousands of seconds. So, yes, so it's very fast. It's designed for performance, and it's designed for the HPC ecosystem. Additionally, we've been able to do some things to help with the facilitation of kernel space and user space incompatibilities. So GPUs are an easy thing to point out here, right? So if you have a container that has a CUDA-enabled application inside that container, and you want to go run it on a GPU somewhere, well, that version of CUDA inside that container is going to require a specific driver running on the host. You may have an incompatibility. So Singularity goes a step further and helps to normalize the environment and facilitate the communication pathway such that you have alignment between the kernel drivers and the library implementation, such that you can gain full portability of your GPU containers. Let's talk about the container image a little bit. So it's designed, as I mentioned before, single file. Right? It's designed for extreme mobility. It's designed for simplicity. You can take this file, you can move it around, you can archive it, and you can manage it like you're managing all of the rest of your data. So if you have a data management policy, right, Singularity is just going to fit into that. Right? If you have controls on your data, Singularity containers are just data. There's no additional network services, there's no registries, there's nothing else you have to worry about. It's just a single file. And it's a single file that's owned by whoever owns it. It's owned by the user, right? Not owned by root. So it makes it incredibly easy to work with. Again, you can share it, you can archive it, it's controls compliant, and again, it's just data. And this means that it's just a file in your system. You can just change your permissions on that system to give access to different users. All right, now lastly, in terms of the integration, you have to be able to integrate with your underlying architecture. The HPC systems architecture you need to be able to integrate with. So that's things like MPI. So right at the beginning of creating Singularity, I had a proof of concept, and I started calling all my friends and whatnot that are MPI developers. And I said, you know, I got this problem. I've got a container system, and I've got no idea how to run an MPI workflow through it. You want to come out and hang out, and I'll buy beers? And that's basically how we figured out how to run MPI through containers. A lot of beer. Highly recommend it. Next is resource managers, right? You want to make sure that you can support pretty much all the resource managers out there. And how do you do that? Well, you don't integrate directly into the resource manager. You make it really easy for users to include the Singularity commands in their batch scripts. And it makes it's incredibly simple. So let me give some examples. First off, native host integration. All right, so if you go into a Singularity container, and the exec verb for Singularity will basically just run a program within that container. So if I do Singularity exec pointing at a container image, and then say pwd, well, that tells me my parent working directory, tells me what directory I'm sitting in. Now, I'm going to end up inside that container, sitting in the exact same directory that I'm in outside the container. So this means that whatever data is in your current directory is going to be data that's in your container's current directory, right? So we're going to blur the line between what's contained and what's not contained, what's on your host. This allows us to now do something like this. We can do a Singularity exec, and we can run the version of Python inside that container, right, on a script and data outside that container, and run it incredibly easily. We could do the same thing with pipes. So if you have a pipeline, again, it passes right through Singularity. If you're using a batch scheduler, just put your Singularity command into your batch scheduler, into your script, into the batch script. All right, this one is talking about an MPI example. I mentioned MPI before. All right, so if you basically have an MPI workflow and you're running on an HPC system that has an MPI on that HPC system, well, that MPI on the host knows how to communicate with the resource manager. Right, so you want to use the MPI first on the host. That's going to then trigger Singularity. Singularity will then trigger the MPI inside that container. The MPI inside that container is going to link against the libraries inside that container. Those libraries are going to reach back out and call the outside MPI, right? And they're going to do that wire up, the handshake right there. So that's a necessary component of this. Now, there's some limitations to doing this, right? The outside MPI has to be somewhat compatible with the MPI inside the container. Right? So there's a little bit of hand waviness going on here, right? So as long as you are running, in our experience from our testing, as long as you're running like, whether it be MPitch, MVAPitch, OpenMPI, Intel MPI, or whatever on the outside of the container, you can do the same thing on the inside of the container. Versions don't matter that much as long as you're using OpenMPI 3.x or newer. And then everything just seems to work. There is a cool project coming out of OpenMPI called PMIX. PMIX stands for the Process Message Interface Exascale. And if you're using that, you can basically forego the outside MPI, not have to worry about any of those layers of compatibility, and everything just works. And for GPU and CUDA support, this is what that looks like. You just basically pass the NV option, and Singularity will know how to figure it out. So DK's talk, he had a bunch of performance stuff in there, and one of the benefits of not presenting first is I can update while other people are presenting. So I saw he had a bunch of really cool graphs and whatnot, and I said, hey, I need some pretty cool graphs. So I threw a couple in there. And this one is actually from DK's group in Ohio. So what you'll see basically is what we're demonstrating is that performance of a container system, in this case Singularity, was pretty much giving native performance. Right? We're not seeing much of a difference. As a matter of fact, in some of our own testing, we've seen differences that are more associated with the versions of the libraries in the container. So for example, at some point we did a test with Red Hat 7X, I don't remember what version it was, and then did another test with on the host, it was running Red Hat X-1. I don't remember what version. Let's just say it's 7.4 on the host and 7.5 in the container. 7.5 in the container actually ran faster than it did on the host. Right? Because we had newer OFED libraries in there. So we get some really kind of cool, peculiar, interesting effects as soon as you start swapping out that whole user space portion of the operating system. Network performance, this is from San Diego Supercomputing Center. See again, pretty much the same as native. Latency. This is done by Dell's Innovation Labs, LS-DYNA performance. You'll see again, pretty much dead even with native. All right. Let's talk about security. All right, security is a hot topic when we talk about containers. So first off, when I talk about security for containers, I like to focus on three separate areas. The first one is the container engine itself. So first off, Singularity is designed not to have any root-owned daemons. Right? So there's been a lot of talk within the community recently about not supporting and not having root-owned daemons. So that's one of our design tenets right from the beginning. To use containers, you have to have some form of access to privileged system calls. You have to do some things on the system that are normally reserved for privileged processes. Traditionally, there's three ways of doing this. The first one is something called the user namespace in Linux. This gives you the ability to run certain system calls under a protected namespace. Another one is you can just run a root-owned daemon and then allow unprivileged users to communicate to this daemon and have the daemon run jobs on behalf of those unprivileged users. Or you can have a setUID component in your workflow. Singularity does the first and the last. We don't have a root-owned daemon. Root-owned daemons, in my opinion, are extraordinarily hard to secure. On the other hand, user namespace, fantastic tool. But not all kernels we found support this. And when they do, they don't support them evenly. We've had some difficulties between the different implementations of user namespaces. Whether you're going from Red Hat, whether you're going to SUSE, Debian, or Ubuntu, they've all implemented it kind of different. Right? So, and we're leveraging some of those differences in Singularity quite a bit. So we've had mixed results with the user namespace. But if you are extraordinarily security conscious, you can definitely use that. We tend to prefer the setUID method. And we've done everything that we can. You know, I can see the system administrators here going, oh my God, it's setUID, right? But we've done everything we can to mitigate any security issues associated with that, including created a way of doing a privilege separation thread and then have a secure API between the two processes, the two parent-child processes, to actually engage in a security-minded way of doing this. We've now had some audits done of the source code. First one was US Department of Defense. Singularity right now is the only container system that they have certified for use on their systems. We have, there was an audit in Europe by a lab who requested not to take on the liability of saying that Singularity was secure, but they said that Singularity was secure. Just don't tell them just don't say which lab it was. All right, so we also have an NSF-funded grant currently doing yet another security audit of Singularity. And so far, by the way, the first two we got thumbs up on, obviously. Otherwise, I wouldn't mention it. I'd be embarrassed, right? I'd hide it. But no, we got thumbs up on those. Okay, so that's the first one. When we're talking about security, we talk about the container engine. Next, let's talk about the container itself. All right, so what does security mean when you're talking about containers? Well, to me, it means trust. It means you can trust that container, trust the contents of that container. Right? As I mentioned earlier, or alluded to, there's a big, huge exploit right now going on against runc, against Docker, against some of the other container systems. LXC is also affected by this. And if you choose to run a container as root, a privileged user, and run an untrusted container, well, let me back up. Any system administrators in the room? Anyone who's ever been a system administrator? A couple people? When you're logged in as root, do you download random code off the internet and start running it? Right? That's what this security exploit is basically doing. And that's what most container systems basically do. Right? They're running untrusted containers as the privileged user. So Singularity looks at this and goes, yeah, no, we've been saying this for a while. Don't do that. Bad idea. If you happen to do that with Singularity, we're just as vulnerable as everything else. Right? But we're also giving a few different mechanisms such that you don't have to worry about this, like cryptographically signed containers with auditing trails and accountability. So one of the features that we have, that if you're going to run a container as root, why not run one that's been cryptographically signed, trusted, and you feel comfortable with it? So anyway, container engine, point of security. Container itself, point of security. Last one, whenever you integrate into an environment, you have to be able to deal with the security measures there, right? So HPC systems, we typically have maybe 10, 100, 1,000 users of these systems. Do we ever give them root? No. So we have to allow these users, these untrusted users, the ability to run untrusted containers, right? Because we're going to let them bring their own containers. They may or may not be signed. The system administrators may not have vetted them. And do that in a trusted way. And that's what Singularity is designed to do. So we are designed to integrate with these fairly complicated HPC environments. Oh, and how do we do that? All right. When a user enters the container, right? If I type in, and I'll show this in just a moment, when I type in Singularity shell, pointed at a container, and I hit who am I, you're going to see I'm the same user inside the container as I was when I started the container. And let me show the example now. Let's say I brought my own container to this system. All right? I created this container on my laptop. I know the root password, right? I shouldn't be able to get root. I installed sudo. I still shouldn't be able to get root. I have a root exploit. And while that's not really a root exploit, believe it or not, this has actually been responsible for breaking into several of the container systems that tout themselves as super secure. That one simple command. So you have to be able to mitigate even security issues inside that container and block privilege escalation. I can't say that Singularity is always secure and it'll always stop everything. I'm not going to say that, of course. If somebody did say that, don't believe them. Right? But I can tell you that all of the security, root level security attacks that we have tried were properly blocked. So this means that it's actually safer to allow your users to run in Singularity containers than it is to allow them to run on the native host. Kind of an interesting paradigm shift there. Additionally, again, we take security extraordinarily serious. So we even have additional security features. First off, and this just goes without saying, system administrators always in control. System administrators can decide what happens with the container system and what doesn't happen with the container systems, what the users are allowed to do and what the users are not allowed to do. All right, already talked about user namespace. We happily love to support the user namespace when the user namespace is present on the system. We also support Linux capabilities. Right? So by default, we're going to drop all Linux capabilities when we enter the container. If the system administrator decides that a user or a group of users can have some additional some additional Linux capabilities, well, Singularity has a mechanism to basically do Singularity capability add this user. And then you can add a list of capabilities. The root user can do that, by the way, the system administrator. We directly integrate with the host's SE Linux, AppArmor, or SE Comp. Right? We have profiles for each of these, and you're welcome to tune those as you like, but we give some sane defaults. And container execution could be limited. So if as a system administrator, I say, I'm only going to allow users to run containers on this system when those containers have been vetted by my security group. All right, so I can say in a configuration file, I'm only going to allow containers that have this fingerprint in their signature, a fingerprint that I trust. All right? Or I can put those containers into a trusted location on the file system. Or I can say I'm just going to trust containers that are owned by a particular user or by a particular group, or set of users or set of groups. All right? So we're giving a huge amount of flexibility. Let's talk about what's new, what's coming. So anybody here currently been using Singularity for any amount of time? A couple people. First off, we updated the back end of the code into Go. You guys hear of Go? It's this new cool programming language. Yay, Go, right? We've updated into Go. It's kind of a mixed bag for me. I really like what it's been able to provide for us into a code base, but I'm just way too old to start learning yet another programming language. So I I am no longer a core developer of Singularity since we moved to Go. Every now and then, though, I'll play in the C stuff, and that's about it. But we've moved to Go. We've also adopted complete OCI compatibility. So you'll see this in several different fronts. First, there is a Singularity OCI verb, at which point we've supports now all of the OCI commands with that verb. We also have OCI integration with the container format. So if you have a OCI container, whether it's in Docker, whether it's in one of the other OCI compatible formats, not a problem, we support it completely. We also support, by the way, OCI at the library side. So if you want to link directly into our libraries, or you want to run a gRPC service that I'm going to talk about in just a moment, you can link directly into Singularity that way as well. As a matter of fact, that's how we're doing Kubernetes. Let's see. Enterprise standards. OCI, the Container Networking Initiative, or Interface, excuse me, CNI. This gives us access to do things like port mappings, binding ports, doing port forwarding and whatnot, networky, cool networky type stuff. And C groups, if you want to have further resource limitations. I already talked about CIF, so I'm not going to go into that as much. Multi-stage builds. This has been a huge request for a long time. And if those of you who are building containers and have gone through this process is probably already familiar, the idea of a multi-stage build is, let's say, for example, I have this little piece of source code, and I want to compile that piece of source code. But to compile that, I need all these development libraries and development tools and a tool chain and all this stuff, which makes my container like 5 times as big as it needed to be. And then I compile this, and now I have this giant container because I'm carrying around all these development libraries. Well, this would allow you to basically do that development in a temporary layer. And then as soon as you're done with that, you just pick and choose what you want from that layer to go into your final container, and the rest of it just disappears magically. So multi-stage builds. This gives us the ability to support things like HPC, which is NVIDIA's container management and build tools. Also, we had a great talk from Todd this morning, or this afternoon, about SPAC. Right? We can integrate with SPAC, we can integrate with EasyBuild, as well as some of the other container builders out there. Right? Like first off, Docker, but image, Builda. So it gives us the ability to integrate directly with these. Native support for Mac OS and Windows. Anybody want to run Linux containers on your Mac by chance? A couple people, yeah? What about Kubernetes? Anybody been thinking about Kubernetes for their compute workload? Yeah, a couple people. Kubernetes really opens up some interesting use cases and workload options for compute. I'm going to talk about those in just a moment. Singularity support on Mac. That's not an edit, that actually really works. Right? Singularity, you install it and you just do Singularity shell, pointed at a container, as a local container like CIF, pointed at a Docker URI, pointed at any container, and boom, you're going to be basically running it. It takes a little bit longer to spin up on a Mac than it does in Linux. In Linux, I mentioned it's in the thousandths of seconds. On the Mac, it's about 1 to 2 seconds. To hit enter, you have to wait a second or so. But then it gives you actual Linux. You're now running Linux. You can even run X apps through it. You can run all sorts of really cool stuff through it. Right? But all of a sudden, you don't need, in case you're curious now, you don't need a hypervisor on your Mac anymore. Right? You just type in, just go get Singularity, and you can run any Linux distribution you want. And if you want to build SPAC containers, well, the home directory is seamlessly transitioned from your Mac into your container. So you can just start typing SPAC install and whatnot and start building up your environment. Right? Incredibly, incredibly easy. Kubernetes. Kubernetes is doing something really interesting because it is bridging the HPC community to the rest of the world, right? And it's giving us some really cool options. By the way, that's one of our core developers, and thank God he didn't die because, yeah, that's Michael. So on the YouTube video, everybody, hi, Michael. But we're working with Kubernetes. We're also working with HashiCorp's Nomad. Anyone familiar with Nomad? Hear of Nomad? Cool, a couple people. This is really interesting because it gives us the ability to focus on new types of compute workloads, right? We don't just focus on the traditional HPC. We're doing compute in general. any sort of compute workloads. HPC is the big, huge, lion's share of compute today, but we're seeing a massive adoption of compute-based workloads in non-traditional compute settings. All right, we're seeing it in AI, we're seeing it in data science, analytics, and we're seeing it being done by enterprises that have no experience doing compute. All right, so we have a wealth of knowledge that we can be sharing and bringing to this community. But going back to the point, artificial intelligence workflows, they're not exactly like what we've been using in compute, generally speaking. We have a build and train, and we have a distribute and run and infer, right? The inference doesn't always, as a matter of fact, most of the time it doesn't happen on the same resource that you're using to train, right? Depends on the workload, of course. But we're seeing a lot of people actually doing the inference all the way out to edge or towards their detectors or whatever their sensors are. Right? But the training for those, you need some dedicated, big, huge resources. So this is kind of an example of how I see this. Right? Starting with the HPC system, whether you're using SLURM, Univa, pick your favorite scheduler, or Kubeflow. Right? Kubernetes is really good at services, but Kubeflow is a little bit better at jobs and batch jobs. All right, run that through your schedule, through your HPC resource. Right, you could be using MPI, or you could be using Horvad. Containerize that trained model. Bring that trained model up to, it just so happens we have a service called the Container Library, which hosts data, containers, and trained models. Weird, it's coincidental. Bring it up to the library. And then from there, you can actually distribute it out and run it, and distribute it via Kubernetes and run it all the way out to the edge. So this is a really cool workflow that we've actually been speaking with a lot of people about, and not just the traditional non-traditional compute, enterprises, but there's actually a lot of, HPC labs that are really interested in this. We were speaking with one lab just recently that has a big, huge detector with thousands of data streams coming off of this as they're searching for things like gamma rays and whatnot, right? And each one of those data streams is too big to actually persist to disk, and they need real-time analysis of this. Well, using this model is the perfect way that they can do real-time analyzation of that. And of course, got to show some more performance graphs. This one is GPU comparisons through TensorFlow, native and contained. Anybody go to supercomputing? A couple people, okay. So at the last keynote, Jensen, CEO of NVIDIA, spent about 25 minutes talking about Singularity and Singularity-enabled workflows in his keynote. I'm seeing a couple people nodding. Yeah, I wasn't even there, right? I didn't even know this was going to happen. So I'm actually somewhere else. All of a sudden, my phone just lights up of like 8 or 10 people messaging me simultaneously. Dude, are you here? Do you know what Jensen is doing? It's like, no. What's he doing? He's talking about Singularity. Whoa, they support Singularity. Whoa, there's a demo. You should see this. Oh, okay. NVIDIA now supports Singularity in their cloud and in other facets as well. At Supercomputing, we also won some awards. I got 3 HPC Wire awards this year. That's a portion of the team that I brought with me to Supercomputing this year. In addition, we've had massive adoption throughout the HPC and compute ecosystem in general. As of Singularity 3.0, and these are hard numbers to get, we can account for multi-million of container runs per day. And the way we know this is there used to be an online just voluntary registry that people would just submit their systems to and contact us and let us know this sort of stuff. But now we also have customers. And customers, we just get to know that stuff. It's kind of cool under NDA. I had no visibility, no idea that people with these gigantic systems in, let's just say, oil and gas and other things, they've got really big systems. Coming from the government labs, I thought those were big. There's a lot of big systems that are not widely known. Just leave it at that. And again, DK, thank you for putting out your number there of downloads. It makes me look small now. We only have 250,000 of downloads. But we are trying to catch up, and the project's only 3 years old. So maybe within a few more years we'll catch up. Although DK, your ramp is going up, so maybe hard to catch. And we're installed on over 5 million x86 cores and about 250,000 ARM. Now that's a really interesting number because we're seeing the uptake of ARM going up real quick right now. So we've got some cool press going on too. Not going to go through each one of these. And this was really cool. CRN touted us as one of the top 10 container startups of 2018. And there's some really awesome names on this list with us, so this is something we're really proud of. Okay, I just had my engineer hat on. I'm going to take it off now, and I'm going to put on my CEO/salesperson hat, right? So we're doing some things to make money, to pay for all this stuff. And out of that, you know, a couple of these things are obligatory, like we have support, we have professional services, we have user education, workshops, that sort of stuff. But we also have some licensed products. So one of those is Singularity Pro. We have Singularity, you know, base Singularity Pro, which is basically the version that you'd get, you know, if you download, you know, from the GitHub, right? We basically have a commercial spin of it, and we support that professionally. But also Singularity Desktop. I showed you the Mac running before. We got some more products too that is not labeled here. That if you're interested, I'll be happy to let you know. And these will be released probably by the second half of 2019. I can give some hints. Right? We just saw some cool Kubernetes stuff, right? We also have a cloud service called SCS. There's the key store, there's the container library, remote builder, and a DevOps-focused CI/CD workflow pipeline that you can run on top of all of these. So you can have an entire CI/CD pipeline associated with the development and management of your containers as they go from develop to production. By the way, the container library is also in charge of archiving and hosting these containers. Something we're seeing a lot of is in, you know, as an example, pharmaceutical industry has FDA regulations about reproducibility whenever software is being used as a medical device for either the diagnosis or treatment of illness. All right, so this gives us some really cool benefits specifically for Singularity here. And of course we can, you know, we can sell all of that cloud stuff that we're building for on-prem. So those of you who, you know, want to run that on-prem, be happy to license that. Got to show my team because this is definitely, all this awesomeness is not coming from me anymore. I might have started it, I might have got the ball rolling, but I have hired people that are much, much, much smarter than me. Thank goodness. And so this is a group of the developers. We are, at the end of this month, we should be over 30 people, and we are just over a year old. So we've been growing like crazy. If people are interested, please let me know. Always looking to hire fantastic people. We have a Singularity user group coming up. When I mentioned at the beginning of this, I talked about running an event. Oh my gosh, it really is a lot of work. So we have a Singularity user group coming up next month. Call for papers is still open for like one more day. So if you want to present, if you want to be part of what we're doing, please submit a paper. Information should be for this should be really easy to find. It's in March, and we're going to be hosting it at San Diego Supercomputing Center. So please join us. And I ended up putting a slide in here because I always bring lots of swag, shirts, stickers, and pens and stuff, and then I forget to tell people that I have them. So then I go home with just as much as I brought. I got a box of stuff. So if you like Singularity, you want to help, you know, put some stickers on your laptops or have a shirt or some pens or something, please let me know. So with that, that is the end. Are there questions? Yes?
If malware was running in a Singularity container, would it be able to escape the container and infect the underlying system?
The question is, if malware was installed inside of a container, could it infect the underlying system? The question to me is, what user is it running as? If it's running as a non-privileged user, the worst that it can do is infect the user's home directory, right? And permission, because we're not giving any extended privilege. So if you run a container as root, and this goes back to the security issue that's happening right now, right, regarding the Docker Doomsday, which basically is that you're running containers as root, and inside those containers there is malware. And that malware is actually exploiting a portion of the runc code, and I don't want to blame runc. It's across all of us. It's a cross between a bug in the kernel as well as a bug in the container runtimes. But basically, it's exploiting that. So then every container you run after that is basically propagating either that bug or something else. Yes, is the short answer. But it depends in terms of who's running it. And this is why we're spending so much effort focusing on how do we trust what's inside those containers. And if somebody finds malware in a container, what can we do to mitigate and control that blast radius? Right? So one thing that we're doing in that case is we revoke those keys. So as soon as you revoke those keys, all of a sudden, people that are, you don't have to force that every container you run will check the keys, but you can do that as a system administrator. And in that case, we revoke those keys, render them unable to validate the container, and all of a sudden things will start failing, and we can control that blast radius.
So the scenario I was thinking of was not running as a privileged user, but as a regular user. Would there be any way to control what part of the file system?
Oh, yeah. Yes. Yeah, there is an option to Singularity called contain and contain all. Contain versus contain all just basically defines how much of the host-based operating system are you containing. And as soon as you use those features, yeah, in this case, you actually would have no issue. It would properly secure you, and you wouldn't have to worry about the malware. What you would have to worry about is while that container is running, that malware may also be running. All right, so if there's let's say a cryptocurrency Trojan inside that container. By the way, this is a real thing. It's kind of an interesting exploit if people were following that epidemic through Docker Hub not too long ago. There was a cryptocurrency mining Trojan that basically went into Docker Hub. People downloaded that container. That Trojan would infect the root running Docker daemon such that every other container that was run was also now infected with this cool Trojan that was making somebody a whole bunch of cryptocurrency. It's kind of cool. I mean, I'm sorry, it is. I know it was bad, but it was not me, I swear. He got in trouble. Didn't quite make as much as I think he thought he was going to. But anyway, while the container's running, yes, this thing might be going. And this is, again, why it's so important to trust your containers. And how do you trust those containers? Well, the only way that I know of at this point is to either trust exactly where it's coming from, right? So if you're going to download a container from NVIDIA's GPU cloud, NGC, right? You have pretty high confidence that you can trust NVIDIA. Well, I don't know if you can trust NVIDIA. You have high confidence that those containers are coming right from NVIDIA. You can trust those, right? If you're going to Docker Hub and you're pulling from whoever's repository, you have no real data in terms of what did they build from, what's in that container, and whatnot. You can kind of go through and rebuild pieces if you're that diligent. But most people that run containers as root, historically, are not that diligent. Right? It's kind of lazy at this point. So, but if you run it as a regular user, a non-root user, right, and you contain all, that's how we recommend to handle untrusted containers, completely untrusted containers. Yes?
I have two questions. The first question is about signing and trust. Do you have a root trust system where if somebody were to download it from NVIDIA and then intermediate then gets to you, can it be falsified?
So the signature, so at the moment, we are the root host, I guess you could say. Not a root trust, but a root host of the container. We're working on how can we become an authority for these, but again, it's about who are you granting the authority with and so on and so forth. So at the moment, how it would work is if NVIDIA, we use them as an example, were to build a container and then sign it, they'll take their public keys, they'll push it to our cloud library, our key store. And then it doesn't matter how you get the container. It can come directly from them, it can come from email, archive, whatever. You now do a Singularity verify, and it's going to contact our resource and verify That protocol is using the standard HTTP key protocol, so it's HKP, which is PGP's standard protocol. And so you can also implement this with any standard HKP service that you want, and you can run that on-prem. We're also working with getting it to work with HashiCorp's Vault. So some cool stuff there.
Just follow up on that question. Our cloud has a problem of having internet. I mean, sorry, our cluster has a problem having internet access. So
Yeah.
admins won't let us, won't open any for us to verify. So how would we go about? So you mentioned about we can verify like a trust like group. Right? So can I like assign like 3 special people that
Yep.
only have the power to sign, and then that could be locally trusted?
Yep. Yep. And you can also verify, I don't know how you normally bring code into that system. If it's through another, like a DMZ or something, some other trusted resource, but you can do the signing, the verification there, and then just know when you copy it over, it's still the same container, the same data. But yeah, you're right. We've dealt with some of the labs out there that have extraordinarily tight security, and yeah, air gap is one of them.
Okay, this was my second question, because that was just a follow-up. We have also problems with kernel drivers, and I know there's micro OSs that kind of have a containerization, the kernel, the whole stack all the way from application.
Yep.
Would it be possible for Singularity to maybe for right now have a path to containerizing the kernel space? Is it possible? Would you guys be looking into containerizing, not crossing the kernel to user space, but just containerizing the kernel space?
The only way I know of how to do that is through a lightweight hypervisor. So you can basically run a second kernel. We are looking into some of that. I mean, as you can see, I mean, I just showed, it wasn't really a demo, but I showed a screenshot of it running on the Mac. I mean, you have to do some of that in order to get it to run on a Mac or get it to run on another operating system. And as a matter of fact, we are looking into and we're deciding how best do we manage the most secure of conditions. So Intel has Clear Linux, for example. That's one of the ways that we are considering following suit in that, basically. So there was another question over here.
Yeah, I was curious if you considered Rust as an alternative.
We considered a few different things, and I was very resistant to move it away from C. The reason why we went to Go is because so many of the other ecosystem libraries and tools are also written in Go. So there's things like, Kubernetes, there's OCI, the OCI libraries, there's a CNI library, C group libraries. All of these things already written in Go, and it was really easy to integrate with. And Kubernetes, of course. Are there any other questions? Yes?
Are there any kind of repositories of these sort of popular things in your SIP format that are hosted by your company or by others?
Yes. That's a fantastic question, especially considering we're here at Stanford. Stanford has invested in actually hosting something called the Singularity Hub. It's maintained by Vanessa Sokat, and she does a fantastic job maintaining the hub. And there's thousands of containers up in there. We have our container library. We haven't released it at this point. It's focusing on a slightly different side of the container hosting problem. And so for example, Singularity Hub is integrated into GitHub. So as soon as you commit to GitHub, boom, it automatically builds a container via CI/CD, blah, blah, blah. We want to treat containers like black boxes. Right? We don't want to have an automatic builder, force an automatic builder. I want, if somebody creates, this container, honestly, I don't care what's in it. Now, I know that this is kind of, opposite of the security side, but if I trust that person, right, it shouldn't need to go through an automatic builder, right, especially if it has commercial or proprietary code in it. And we do support private repositories as well. So as long as it's signed by someone I trust, that's what's important to me, not the fact that I built it. So slightly different, but yes, there are hosting platforms out there that are not us.
That your library will be sort of a commercial offering?
Think of it like a cross between Dropbox and GitHub model. So it will be free to use, even with some private repositories. But if you have giant amounts of space that you want to host up there and whatnot, we'll give allocations to large academia or to academias who needs large amounts of space and whatnot. But for the most part, that's one way that we're going to be paying for this. And it's hosted in, public clouds. And you might know they're really expensive when you start talking about data transfer costs. So that's our model there. That's our business model there. Are there any other questions before I get pulled off the stage? All right, well, thank you, everybody.